Okay, so I think let us slowly start today's session. So this is the week 7 content. So have you gone through the videos?
Yes, I have gone through
Yeah.
uh, this diagonalization and its applications.
Hmm.
So, uh, there, sir has told about that curves and all quadratic curves and how to like make a symmetric matrix out of it and like do the translation and rotation and and he has solved one problem also.
Yeah, actually, this is like linear algebra is very important in mathematics. This like whatever we are studying, basically we concentrated on Rn only. Like while studying the vector space, I think in the next week the vector space everything is like general vector space and everything is coming. So yeah, whatever we have studied till now is a very basic concepts of linear algebra, and this linear algebra is a like used in it has various application in different fields like differential geometry and all. So and one more application, that application of spectral theorem also he was mentioning in the class, right?
Yeah,
Yeah.
spectrum.
So today actually application means in the pure, if you are studying the pure linear algebra, like basically the exam also I think mostly concentrated on the, yeah, pure concept, eh? So in this last week I haven't seen much things in the week, so I will start with some applications of spectral theorem. Okay,
Mm.
and that quadratic thing and all, like actually he has done one question, so everything's like all the questions are similar kind of repeating, and it is like mostly related to geometry and all. So I'm not going to those kind of questions. We will solve something related to spectral theorem, and then we will solve something diagonalizability and all. Okay.
Yeah, thank you.
Yeah.
So my one more thing, this assignment 7.
Hmm.
So in the week 6 we did diagonalization and all that. So the assignment 7 is related to similar diagonalization only.
Yeah,
Uh,
mostly related to week 6 only, है ना? हाँ.
then it has a lot of thing with the upper triangular matrix. Two questions are where upper triangular matrix is used, and then one question is on similar matrix, which we covered, I think, in the class also. So that is easy, not difficult.
Okay.
But the other questions, I'm not getting any basis to say this is why I am answering like that, because like transpose, like say transpose is used instead of inverse. And so intuitively, if I take an example, I can say, okay, this looks like true, but I have no basis to claim that, no theorem and all, like to say, oh, because of this, this is true or this is false. Yeah,
Yeah, basically like most of the questions are true or false, right?
yeah, yeah.
Yeah, basically the thing is uh,
Because
you have to
in
find the
the
counter
assignment.
example.
Mhm.
uh, like I don't know the questions exactly now, and even I cannot discuss
Okay,
the questions now. So the thing is like
okay,
you can try to
okay.
find
So
the
fine.
counter examples first of all.
Next time I'll clarify with you.
Yeah.
If there is something, I'll put it on the discussion also.
Okay, okay.
Uh,
Or you can discuss in the
so
next week this live session. One
yeah,
more. Yeah.
yeah. One question I have,
Hmm.
like in one of the lectures, sir has told in the first lecture he had told that P inverse AP is equal to D,
Yeah.
right?
Huh.
But in subsequent lecture, like in where he was telling about quadratic thing,
Hmm.
so there he has used P A P inverse is equal to D. So is that like something we can take it as equivalent or how it is?
Yeah, both are same actually. See, what he was
Oh,
saying is
hmm.
P inverse AP. Is my voice is echoing?
No, it's not echoing, but in between it is going like little bit cutting off.
Okay, okay. Yeah, yeah. Please let me know if you have some trouble, like too much
Sure.
Yeah, okay. So what he was saying is P inverse AP equal to D, like correct? And you are saying equivalently he is saying PA P inverse. What is it? Correct?
Yeah. Yes, yes.
Okay. So
Yeah.
the only thing is if I am taking P inverse equal to Q, what I can write the first equation, one will become QA Q inverse equal to D. Correct? So that is what exactly this equation means. Means this P and this P
Okay.
are not same actually. It's just a representation. There exists a matrix means like P inverse AP. If I am taking the inverse of the P inverse, then I can write it as P, right?
Yeah.
It is just a representation. Like it is not like P and P inverse are equal. Instead of P inverse, we are writing P inverse as the matrix and the like P inverse as Q, and hence we can write
Mhm.
QA Q inverse equal to D. That's all.
So why do we need to do this changes? Like, in what scenario this trick is required? Um,
Uh, so,
because in the today class
hmm,
he has multiplied the xy with and then again with xy in the quadratic thing,
hmm,
and there he has used. So I'm going to the notes. Just a second. Yeah. So yeah, there he has uh, used this interchangeably. So, is there any particular scenario in which this kind of trick will be used?
that
Like where we want to assume P inverse to Q.
no, maybe like it is just like maybe he may be using it to prove in such a way that like if he
Hmm.
needs some particular proof or something, he may be just interchanging in such a way that it is not affecting. Like if he is taking P inverse AP
So,
in the beginning, then he will not take after that P A P inverse because that P is same at this point, right? But from the
yeah,
beginning itself, if
yeah.
he's starting with the P A P inverse, okay, that's fine. He can continue like that.
Yes, he has done that only. Like he just stuck with one only. But my
Yeah.
question was more like, if say we use either one of them, so it is mainly for proof purpose, right? Like say I want to prove something, so I can start with either one of them and
Yeah, you can
that's
start
it.
with the, like that is not an issue, but the definition, what is the definition? If it is diagonalizable, there exists a diagonal matrix such that P inverse AP, like the what standard
Yeah,
definition is starting with the P inverse AP, like that.
yeah.
P inverse AP
Okay,
equal
fine.
to
So
D
that,
and A equal to PDP inverse. That is why, that is how we use standard definition.
yeah. Okay. Yeah.
Okay.
Thank you.
Okay, then let's start with some questions today also. Okay. Okay, so one main application of the spectral theorem was to find the powers of the matrix. That is what we started with. Okay, so first question is, okay, if let A be a 2 by 2 matrix, A is given by 5, 6, 3 minus 2, find A power 100. So, do you have any idea how to find A power 100?
Yeah, I mean, this one, as told in the lecture, A raised to 100 is equal to P D raised to 100, P inverse.
Yeah.
The once we find D, it will be just a multiplication of the diagonal elements.
Yes, so what we need to prove is like if A is not diagonalizable, it won't be that easy. Correct?
Yeah, yeah,
So the thing what we need to find is to check is A is diagonalizable or not. So so we will start with the determinant of A minus lambda equal to 0. So first thing is we need to check it is diagonalizable. So what we will do, find the eigenvalue, and eigenvector, and we need to find the p also, the matrix p also. So determinant of a minus lambda I means 5 minus lambda 6 3 minus 2 minus lambda equal to 0. Okay, so maybe I can leave the calculation part and I will write the final equation. Okay, so what we will get is lambda minus 7 into lambda plus 4 equal to 0. So this is our characteristic equation. Okay, so what are the eigenvalues?
This 7 and minus
Yeah,
4.
lambda equal to 7 and lambda equal to minus 4. So how should we find the eigenvector corresponding to lambda equal to 7?
Yeah, just 5 minus 7
Yeah,
minus 2, 6, 3, and minus 9
yeah, minus 9. Okay,
into x1, x2 is equal to 0.
equal to 0, and we need to find the solution space of this particular equation, correct? So what is
Yeah.
this equation says? Minus 2x1 plus 6x2 equal to 0 and 3x1 minus 9x2 equal to 0. So this is just exactly same equation, like just a multiple, right? You can
Yes.
observe that. Yeah, we can write it as minus x1 plus 3x2 equal to 0. Fine, or x1 equal to 3x2.
Yeah.
So what is the eigenvector? One eigenvector?
Uh, 1, 3. Uh, so 3, 1.
Yeah,
Not 1, 3.
3 1. Corresponding to lambda equal to 7 is
Yeah.
3 1. And in the same way, yeah, let's quickly do lambda equal to minus 4. So this is our A minus lambda matrix, and lambda is minus 4. So what is the matrix now?
9, 6, 3, and 2. 2.
9 6 3 lambda equal to minus 4, right? Yeah,
Yeah.
2. So 9x1 plus 6x2 equal to 0. So this is same as 3x1 plus 2x2 equal to 0, correct?
Yeah.
So what can be the eigenvalue here? Sorry, eigenvector here?
Again, x1 is equal to minus 2x2. So if x2 is 1, then minus 2 and 1.
X1 is?
So if x2 is 1,
Yeah.
then x1 is minus 2 by 3.
Yeah, okay. We can take it like x1 is minus 2. I mean, we can avoid the fractions, okay? So
Okay.
x1 is minus 2, so x2 should be 3, right?
Yeah.
Correct, okay? Yeah. So, if we are taking P as, so corresponding to 7, we got 3, 1. And corresponding to minus 4, we got minus 2, 3. Okay? And what is P inverse? Can you say quickly?
P inverse 3, 1 minus 2, 3. No, I'm just thinking because this doesn't look like orthogonal. Just a second. Uh, no, sorry, I cannot
Adios,
tell.
amigo. Powering on.
Sorry. Is it possible to tell
Yeah.
like just by looking at it? Okay. Uh, minus 3.
The thing is, we are finding the diagonalizability. I mean,
Yes. So
we,
in orthogonal, we just can take a transpose directly, right? But for
okay,
uh,
okay.
this one, P inverse is equal to adjoint of A divided by modulus of A.
Hmm.
So, so determinant of A is 9 minus 9 plus 2 is 11,
Hmm.
and adjoint of A is Just a second. Uh, just thinking because I haven't done too much of adjoint problems. Uh,
Yeah,
so
in 2 by 2 matrix, to find the inverse, you have an easy way actually.
okay.
Like if you have A, B, C, D,
Mm-hmm.
okay, suppose it is invertible, it will be A inverse equal to, okay, determinant of A, you can find it easily.
Mm-hmm.
Okay,
Mm-hmm.
the thing is, what we will find actually adjoint means we will keep A here and then D. Okay, that we will write in the 1 1 position, correct?
Okay.
Okay,
Yeah.
so okay, in the 2 2 position, what will come?
Uh, so
A,
minus.
right?
Yeah.
Minus 1 power 2 plus 2 means 4,
Yes.
and
So
A.
positive A.
Here,
Yes.
uh, see, adjoint means transpose of the cofactor. Okay,
Correct. So
so
minus will go on the right side.
here it
Minus
will be minus B and minus C.
minus C, right? If we take a transpose, A. I'm just thinking.
No, no. Okay, we can just check what is A inverse now. Okay, 1 by okay, what is determinant of A here? AD minus BC, correct?
Yeah.
Yeah, 1 by determinant of A. Uh, Now we are multiplying. What is A? A into A inverse AD minus BC, first term, correct? And
AD minus
second term minus BC, sorry,
minus BA plus
minus BA plus
BA.
BA. Okay,
Hmm.
so
Hmm.
what is the next term? CD minus CD.
Minus
Okay,
C. Hmm.
and the last term is minus
Yeah.
CB plus AD. So what is
Hmm.
this? 1001, correct?
Yes.
These
Yes.
two are becoming 0 and this is divided by the determinant 1 means, okay,
Yeah.
so yeah, you can see the what is A inverse here. Okay, keep the determinant like that, interchange the A and D. Okay,
Okay.
here we are interchanging, and in these two positions what we are doing, just taking the negative sign.
Okay.
Okay,
Okay.
so
Hmm.
for 2 by 2 matrix, that's all, like interchange that one diagonal entries, and
Hmm.
for other just the change the sign. So here it
Okay.
is interchanging means again 3 3 it will come, and what
Hmm.
will come at the 1 2 position?
1, 2, the same thing with negative.
Yeah, that is 2, right?
Yeah.
2, and here it is minus 1. Okay, you can check P inverse P, whether it comes high or not. Okay, so we got P inverse, fine. Now what is A?
Is 5, 6, 3 minus 2.
Okay, A is 5 6 3 minus 2. 1 minute. Okay, what we want to find is A power 100, right?
Yeah.
Yeah. So uh,
A raised to 100 is equal to
P
P.
inverse AP equal to D. What is D?
D is 7
Yeah, 7
diagonals minus 4.
diagonal, and it was what was that? Minus 4, right?
Yeah.
Yeah. So to find the A power 100, what we need to find? P 700 minus 4 power 100, right?
Yes.
Into P inverse. Fine.
Yeah.
So now got P inverse also. What is this?
7 fours are 28 minus 28.
Sorry, what?
20, minus 28 raised to 100.
From where did you get minus 28?
Oh no.
What is the diagonal for a diagonal matrix? Like how we will do the powers if D is a diagonal matrix? What is d square? You can just check what is d square. If d is d1 0 0 d2,
D1 D1 square.
yeah, first term is d1 square, right?
Yeah, D1 square, and then second one is 0,
Hmm.
and then below one is 0 plus 0, and then D square, D2 square.
Yeah. Okay, that is the positive thing about being diagonalizable. For diagonalizable
Mhm.
only, we can just multiply the term. Like otherwise, finding the metric multiplication is a bit difficult task, right? Especially the 100 power means how we will do the a power 100 like
Yeah,
manually.
yeah,
That's difficult. That is why we are doing. Like we just need to find the d power 100, 7 power 0, 0 minus 4. Now we are just remaining with only three matrices, 1p and d power sorry minus 4 power 100
yeah,
and a p inverse. Okay, it is just a multiplication of three matrices instead of the like 100 matrix multiplication. We are doing three, so that is why the diagonalizability is very important when coming to applications. Okay,
yeah.
yeah. So one more thing, like in the class we were discussing, it is like in differential equation, somewhere it is like while finding the solution of differential equation, the spectral theorem is actually used. So for that, you might have seen something like e power ta, e power td, something like that, right?
Yes.
Okay,
Mm.
so okay, do you know about this? How to take the exponential like power of matrix?
Actually, no. But I remember sir has mentioned in the lecture some exponential. Yes, but I don't know. No.
Yeah, actually, what sir was telling is like P inverse AP equal to D, then A equal to PD P inverse, and then E power A equal to P into E power D P inverse, something like this, right? Instead of this, he was using TD. That was the only difference. Like TD means just a constant multiple. That's all. Okay.
Yeah, but how did
Yeah,
we
how
get
it
this?
comes first, let us see the like concept, and then we will go to one question. Okay, now see whatever the, if we have an equation x square plus 2x plus 1. Okay, now if we have some matrix A, suppose this is our function f of x. Okay, now if A is a matrix, okay, we will take with the square matrix. What is f of a? Do you know what is f of a?
Um, Function of x is x squared plus 2x plus 1. So uh, f of a, like we are taking a matrix A and we are mapping it using this quadratic equation.
Yeah,
Uh, so uh, so A has say I'm just guessing actually. I'm
yeah.
not very sure. So A has say many vectors in it. Then each vector is representing this quadratic equation. The transformation is happening using this quadratic. Is
No,
that
no, not like that.
okay?
The only thing is just replace x with a. That is
Okay.
a square plus 2a plus what will be instead of 1 it will come 1 means the unit in the real line. Like correspondingly, what is there in set of all matrices? Identity, right?
Okay. Yeah.
Identity is some kind of analog to 1. Like correct?
Mhm. Yeah.
Identity into A is like 1 into some real number is again that real number. In the same way, identity into some matrix is the same matrix. So that is why
Mhm.
I'm saying I is some analog. So instead of 1, it is I. So
Mhm.
Whatever the equation we are getting, we can, if we have a matrix, we can write like this. Okay.
Mhm.
So if f of x or f of lambda is a characteristic, okay, this is I'm just saying as a note. If f of lambda is a characteristic equation of some matrix A, okay,
Mhm.
then do you know what is f of A? See, this is clear, right? F of A equal to a square plus, this is like just like a power a plus 2 times a plus I, that's all. Okay. Now f of lambda, suppose it is some polynomial like a naught plus a1x plus etc plus a n x power n. Okay. Now f of a, what is f of a?
Yeah, f of a is a square plus 2a plus I, right?
No, no, no. Now
Like,
I am saying f of lambda is the characteristic equation, and sorry, f of lambda is an equation in lambda. This is my equation. A naught plus a1 lambda plus a n lambda power n.
okay.
So here, instead of lambda, what we need to give is a naught plus a1 a plus a n a power n. Correct?
Mhm.
Okay. So what I am saying is it will be equal to 0. That means it will be equal to 0 matrix. That means A satisfies, the matrix A satisfies its characteristic equation.
Mhm.
Okay. Now here see f of A, we will get some matrix. It need not be 0. But if I am dealing with the characteristic equation, then f of A will always be equal to 0.
Okay.
Okay. Okay. Okay. This just I am mentioning. Nothing to do with our scenario now. Okay. Now we were talking about the exponential power here. First of all, if x is some real number, do you know what is e power x in terms of like series expansion, something like that?
Yeah, 1 upon x plus 1 upon x square. This,
No, it is like 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. This like we will call power series expansion. Okay,
okay.
that means if we are writing in the RHS, if we are giving 1 plus x square by 2 factorial, this infinite sum is same as the e power x. Okay, power series expansion. Now, what is e power a?
So same thing. I
Yeah,
mean, if
same
yeah,
thing. 1 plus a square by 2 factorial plus a cube by 3 factorial plus etc. Okay. Now, uh, see, it is going infinitely, a power n, and so and so. Fine.
yeah.
Now, is this possible? Like, if I am giving some random a, is this possible to find a power n, like for any n?
No. If
Yeah.
yeah, these are the
If
powers of a. Yeah.
Yeah, again, if we are finding the diagonalizable, if it is diagonalizable and the corresponding diagonal matrix we are finding, then it is very easy, right?
Mm-hmm.
Yeah,
Yeah.
that is what the spectral theorem comes again.
Mm-hmm.
Okay, now
Yeah.
this is a e power n. Now, uh, mm, what was our P
So
inverse AP equal to D, correct?
yeah.
So, what is a PD P inverse?
Yeah.
Okay, now what is e power m? E power
A is equal to
PDP inverse.
yeah.
Fine.
Mm.
Okay. Now, uh, how can we expand e power PDP inverse using the same expansion?
E raised to
I
p.
plus, this is I plus, instead of a, we have PDP inverse. Okay.
Mm.
I plus PDP inverse plus PDP inverse square by 2 factorial plus PDP inverse cube by 3 factorial, and it is going like this. Fine.
Mm.
Now, what is this I plus? Okay, instead of I can write P inverse. This is fine, right? Now this is PD P inverse. Now what is PD P inverse square?
P d square P
No,
inverse.
the middle P inverse P will be cancelled. So PD square P inverse by 2 factorial. Next one is PD cube P inverse by 3 factorial. Okay. Now let me take P to this side, and remaining is I plus D square by 2 factorial plus etc. and P inverse. Okay. Now what is this? P into, this is the expansion of
E raised to D.
D, diagonal matrix D, right?
Hmm.
Yeah, this is what he was talking. Like instead of finding e power a means so many powers of a will come. Instead of
Okay.
that, we can find, so we started with e power a here and we ended it p e power d p inverse. So e power a
Mhm.
is same as p e power d p inverse.
Yeah.
Okay, so like instead of a, if I am giving ta means it's just a scalar multiple, like some variable or something t. Okay,
Mhm.
it will come p power td p inverse. Maybe you can start like the same step you can follow for that also. It is like easily follow it, just like this. Okay, yeah.
Mhm.
So p power td p inverse. Now finding e power td, is this difficult for you? What is e power td? I plus td plus td square by 2 factorial plus etc. Okay,
Yeah.
this is fine, right? Like
Yes.
the power d power n, what will come d power n? If d is, if d is some lambda 1 etc lambda n diagonal matrix, here it is 0, what will be d power n for any n?
Lambda 1 raised to n.
Yeah,
Uh, yeah.
in the diagonal it is, okay, we can say it is k, d power k lambda 1 power k etc lambda n power k, and here it will be 0. Clear? Okay, now we will do one question on this. So the second question is, given a equal to 3113, calculate the matrix exponential e power ta. Okay, t is some value, like some variable or something. Now first question is a diagonalizable? First of all, we need a to be diagonalizable, otherwise like we cannot use the above result. So by just seeing, like without doing any calculation, can anyone say it is diagonalizable or not? What is the nature of a? I mean, can you see any speciality with this here? It is symmetric, right?
Symmetric. Yeah. Symmetric. Yeah.
Symmetric. So it should be,
Real eigenvalues will
it
be
should be
there.
diagonalizable also, right?
Yeah.
It
Mm.
has like some orthogonal, that was Speckel theorem saying, right? It has some orthogonal p such that p inverse a p equal to d, correct? So it is
Yeah.
diagonalizable. Okay, let us see what is the eigenvalues. Like we need the p matrix and p inverse matrix. So what we will get, 3 minus lambda 1, 3 minus lambda. So if we are equating to 0, 3 minus lambda square minus 1 equal to 0. Okay. Yeah, again, okay, I'm not going to the calculation. So the final equation will come as lambda minus 2 lambda minus 4 equal to 0. Okay. Now corresponding to, of course, there are two eigenvalues. Corresponding to each of the eigenvalue, we have one eigenvector. Now lambda equal to 2, uh, it should be 1 1 1 1. Okay. Okay, we can very quickly go through the calculation now. It should be equal to 0. So what it is saying, x1 should be equal to minus x2. So 1 minus 1. Okay.
Yeah.
Yeah, it is an eigenvector. If anyone is having a doubt, okay, you can ask. This is the usual procedure. Now the next is lambda equal to 4. So when it is 4, what we will get? Minus 1 1 1
Mm,
minus 1, correct?
yeah.
x1 x2 equal to 0. So this implies x1 equal to x2. So 1 1 is an eigenvector. Okay. So we can take it as p is 1 minus 1 and 1 1. This is p, and you can find what is p inverse. Okay. So what was the question? To find uh, e power
Yeah.
ta. Okay. What is e power ta by definition?
E raised to TA is equal to P
Hmm.
into E raised to TD.
Yeah,
Yeah.
into p inverse, correct?
Yeah.
Yeah. So what is d here?
D is 2004.
First one was 2. Okay. First one was 2 and the second eigenvalue was 4. So, okay. Now we need to find e power td. That is I plus td plus t square. Okay. One thing before that I need to say. Yeah. Before that we need to see if d is lambda 1 etc lambda k. We have already seen lambda n. What was t power k? Lambda 1 power k etc. Lambda n power k. Okay.
Yeah.
Yeah. Now we should write this also. E power d is I plus d square by 2 factorial plus dq by 3 factorial plus etc. Okay. Now I is the identity matrix, that is along diagonal it is 1 and other place it is 0. So d is lambda 1 to lambda n and 1 by 2 factorial into d square. What is that? Lambda 1 square etc. lambda n square plus so on. Okay. So what is the first place in the matrix after adding all these one? What is the first entry?
It's like a looks like a long equation 1 plus lambda
1
1
plus
plus
lambda 1 plus lambda
lambda
1
1
square
2
by
factor.
2 factorial plus etc.
Yeah.
Okay. What about the all other entries in the same row? 0,
Uh,
right? Because
yeah.
everything is a diagonal matrix. Only diagonal entries are there. All others are 0.
Mm.
Okay. So all the upper portions are 0. Lower portions are 0. And in the diagonal, so what is the two element? 1 plus, yeah,
Lambda 2
plus
lambda 2 square by 2 factorial.
plus etc. and etc. 1 plus lambda n plus lambda n square by 2 factorial and so on. Here it is 0, here it is 0. Now, what is this 1 plus lambda 1 square by 2 factorial plus etc.?
Again, e raised to
Yeah, e
lambda.
power lambda 1, and this is e power lambda 2, etc., e power lambda n. Okay. Okay, so this is a very simplified case. Like instead of finding e power a, first we have simplified in terms of d, and e power d is very easy to find. Okay. Okay, now coming to the question, we got d is this one. Okay, now what is our e power td, or what is our e power d? If lambda 1, lambda 2, etc., lambda n are eigenvector eigenvalues, the diagonal will be e power lambda 1, e power lambda 2, e power lambda n. So what are all the eigenvalues here? 2 and 4, right? What was d? D was 2004. So e power d should be e power 2, 0, 0, e power 4. That is what we have done in the general case. Is that clear, everyone?
Yeah, we have just put the lambda on the exponents, right?
Yeah, that's all.
Mm.
Okay, as I mentioned earlier, if it is some scalar multiple e power td, it is nothing but e power 2t, 0, 0, e power 4t. So if you want to verify with t, you just start all the procedure with t. Okay, e power at equal to p e power, not e power at, ta. Sorry. E power ta equal to p e power td p inverse. Okay, so it will come like this. So here our e power td will be like this. So the question was to find e power ta. Okay, so e power ta, we already have the p here. Okay, and e power td we got e power 2t, 0, 0, e power 4t, and p inverse we can find. Okay, so you want to do the further calculation here?
Mm, no, I think it should be.
It is
You
fine,
need,
right? Yeah.
yeah.
So it is nothing but I haven't found the P inverse. So it's just the calculation only. So here from P inverse you can write what is P inverse. Okay. And then just substitute here.
Mhm.
Okay. Anyone is having doubt? Anyone? Please let me know if anyone is having doubt. So this is actually not so important for you, as I haven't seen that it is mentioned what is e power x. I think that is not much mentioned in the class. That is why I have given what exactly is the definition. So maybe if you don't want, you can skip. Uh, yeah. So we can see the next question. Okay. So the next question is, so we don't know what is K. A matrix is given 3K 8 8, and it is given as two distinct real eigenvalues. So what should be K? For what are all the values of K, this matrix A will have two distinct real eigenvalues. Anyone can start how to answer the question at least.
Uh, one can be 8 itself, right? Like, because it is symmetric, then it will definitely have.
Yeah, it is fine, but in general, like or okay. Okay, so let me just rewrite the question. If k greater than x, so what is x? Okay, I want all the possible values. That's all. Okay, this is the statement. What is some some real number x? So if k is greater than that real number, it has two distinct real eigenvalues. Okay, so what is the that lower bound such that this k, if we are putting that k, then the matrix has distinct real eigenvalues. Okay, let me ask you one question. How we will find the eigenvalue?
Yeah, by solving the characteristic.
Equation, correct? So we can start with the same procedure. What is the characteristic equation determinant of a minus lambda equal to 0? So what is here? 3 minus lambda, k, 8, 8 minus lambda, and 3 minus lambda, 8 minus lambda, minus 8k equal to 0. Okay, so basically finding eigenvalue is the finding the solution of the this equation in the variable lambda. So what we will get? 24 minus 11 lambda plus lambda square minus 8k equal to 0. Now lambda square minus 11 lambda plus 24 minus 8k equal to 0. Okay. Yeah. Now can you say anything? So this is our characteristic equation, right? Now can you say what should be the condition on k so that it has real eigenvalue? What is the eigenvalue solution of this equation?
Yeah, this b square minus 4ac should be greater than.
Yeah. So how we will find, like if I have a quadratic equation, if b square minus 4ac is greater than 0, then it has two positive real root. Okay. So what is here b square minus 4ac?
121 minus 4 into 24 minus 8k.
Yeah, 4 into 24 minus 8k should be greater than 0. Or 4 into, no, it is enough to solve the given equation. Should be less than 124. So that's okay, right? 4 into 24, 32k less than 121. Okay. Okay, so the calculation you can do further, right? Okay, from this what we will get, k greater than 4 into 24. I don't know whether I have made some mistake or something. So whatever this value, you can give it as x. So question was for some what x is that such that for k greater than x, it has two distinct real eigenvalues. So we got some value, some real number x. Okay, so this is the lower bound. Now when it will have equal eigenvalues? Is that okay for everyone? The last one, and it will have the distinct eigenvalues. Hello?
Yeah.
Yeah.
Uh,
And
distinct meaning like if b square minus 4ac is 0, then it will have only one.
only one. Yeah.
Yeah.
If it is equal to 0,
Mm.
so the eigenvalues are equal. Like only one eigenvalues are there. So that means repeating. Correct? So
Yes.
equal eigenvalues. If it is less than 0, it will have complex eigenvalues. Means that characteristic equation have complex root, right? So that root is called eigenvalue. So it has complex eigenvalues. That's all. Okay. Here. So the next question: which of the following are true? Similar matrices have same characteristic equation. And the second one is if A and B, if A and B are two matrices, it have same characteristic equation. They are similar. And the third question is similar matrices have same eigenvalues. Okay. Okay, so can anyone say about the first one?
Yeah, that they have the same characteristic equation.
Okay, can you give the explanation also?
Uh, they if the matrices,
Are similar. Okay.
actually this was made as a, I don't have the proof steps.
Okay. So proof is nothing. It is just using the definition of similarity. Okay. This what I have written is if A and B are similar. A is similar to B. So what is the definition of similarity?
They have the same eigenvalues.
No, no. Similarity definition by definition, A is similar to B means there exists a invertible P such that B equal to P inverse AP. Okay, like in any way we can write A equal to P inverse BP, like as I told in the beginning, like it is just a matter of taking the inverse of, if I am taking Q, what I can write, B equal to QA Q inverse, where Q is P inverse. Okay, so from this I can write Q inverse BQ equal to A. Okay, so only thing is similar means it should be written in some form. One matrix is written in the form of P inverse AP in the other matrix. That's all. Okay, this is the definition of similarity. When we coming to diagonalizability, what we were actually saying is A equal to P inverse DP, something like that. If we are saying, what exactly saying is that matrix A is similar to a diagonal matrix. Here we are not mentioning like some particular like diagonal or something. A and B are any two matrices. If B equal to P inverse AP, then it is similar. That's all. This is the definition. Now, what is the characteristic equation of B? Definition.
B minus lambda I
Yeah,
determinant.
determinant of B minus lambda I. Now, what should be the next step? Now, there is nothing to use. You can just use the definition what I stated here.
So we want to substitute P inverse
Yeah,
AP?
of course. That is the
Okay.
only thing we are having. So, we should substitute that, right?
Okay.
Okay. D inverse P inverse AP minus lambda I. Okay. Now, can you think how we can extract A minus lambda I? What we
Yeah.
need is, yeah,
In I we can replace with
good.
P in
Yeah,
P
it,
inverse IP.
so what we can write is this is P inverse P. I is nothing but P inverse P. Now what we can do? What is this? Can I take P inverse outside like this? P inverse A minus lambda E into P. Is this possible?
Yes.
It is possible, right? Okay.
Mm.
Now what should be the next step?
We will take distribute the
Yeah, of
determinant.
course. Determinant of P inverse, determinant of A minus lambda I into determinant of P. What is this?
Characteristic equation of
A, right?
A. Yeah.
Because determinant of P inverse is the 1 by determinant of P, since it is invertible. So these two will get cancelled. The first and third term will get cancelled. So determinant of B minus lambda I and determinant of A minus lambda I are same. That is characteristic equation of B is same as characteristic equation of A when A and B are similar. Fine. Okay. Now what about the converse? If A and B have same characteristic equation, they are similar. Can you think?
Sorry, ma'am, can you please repeat what you asked?
The second option B. If A and B have same, like what we have proved is for similar matrices, it has same characteristic equation. And now
Yeah,
we are saying for two matrices, we don't know matrices, two
characteristic equation.
matrices we have same characteristic equation. Question is whether they are similar or not.
Mm.
That means,
So we have
uh,
to reverse this.
okay, it is not true. Can you give counter example? That means there can exist a characteristic equation same, but they are not similar. Yeah, anyone can think about a counter example. It is like consider just 2 by 2 matrices. It is not so difficult.
If the constant changes, then it will like only the diagonal element has the minus lambda. So if the other diagonal has some other numbers, uh, but for the characteristic equation to be same, it has to be same. Even like constant also has to be the same, right?
Okay, I will give one example. Let A equal to 1001. That is identity. And B equal to 1101. So what is characteristic equation of A?
Yeah, 1 minus lambda square.
Yeah, 1 minus lambda square. And
Could
what is the characteristic equation of B?
1 minus lambda square.
Say. So for
Mm,
A and B we have same characteristic equation.
mm.
Now can you think about like whether they are similar or not? That means is there any P such that B equal to P inverse AP? Is this possible? It's very easy because you know what is AB now. What is A?
Uh, 1 0. It's an identity matrix.
Yeah. So what is P inverse AP?
That is also identity.
Yeah. So is this
So,
possible?
so it's not equal to B.
B,
Yeah.
correct? Yeah.
Mm.
So whatever P we are taking, whatever P inverse AP will be P inverse identity P, which is identity. Of course, it is not equal to B. Okay. So they have same characteristic equation, but A is not similar to B, or B is not similar to A. Both are same. Clear?
Yeah.
Yeah, actually, if you are more interested in linear algebra and all, this B is actually called a triangulizable, we will say. Like we have already seen diagonalizability. That means P inverse dp, something writing like that. So instead of P inverse some db, where D is some triangular matrix. Okay, the same way as diagonalizability, we have triangulizability also. So if you are more interested in linear algebra and all, you can check those kind also. Here B will not be diagonalizable, B will be triangulizable. Okay, so yeah, there is nothing more to do with your syllabus, but yeah, I'm just mentioning these things.
So, ma'am, actually in the assignment there are two questions on upper triangular. So
Upper uh,
I'm
I
not
don't
sure.
think that is about triangulizability. I am thinking about whatever they are taking P inverse AP. About this P, they are saying it is triangle, upper
Okay.
triangle or something like that. Correct? Not about A. Whatever I am said is this A is triangle, like upper triangle or something like that. I think in that question, I am not sure. I didn't check very properly
Uh,
on the questions.
can
Yeah.
I just read quickly? I'll read it.
Yeah, yeah.
Uh, says that A is a real square matrix and
Hmm.
is it's diagonalizable, uh, and U
Hmm.
angular matrix.
Upper
Then
triangle. Yeah.
uh, yeah, then is A is diagonalizable if and only if A is equal to E U F. So where U is an upper triangle matrix
Hmm. Okay.
and E and F are invertible. So I mean they're asking us whether A is diagonalizable or not. Uh,
Okay, they are
so
not giving the condition A is diagonalizable.
no, no, it is given. Actually, it's a true and false. So they are saying it's diagonalizable if and only if A is equal to EUF, where U is a upper triangular.
Yeah.
So, like, I have no clue how to solve this, but
Yeah, this I think you can just start with the counter example only, because like whatever I told in triangulizability also, this is coming like P inverse TP, something like this. Here also P and P inverse are coming, not some random matrix E and F.
Mhm.
Okay, so here I think only thing is you can do is like try with the counter examples. Like if one is getting, try some other way. So that is
Mhm.
the only way possible, I think. Now,
Okay.
okay,
Mhm.
maybe you try, and we will
Yeah.
discuss maybe next week if you
Sure.
are not able to solve it.
Yeah.
Okay. Yeah, so we can go to the next problem. Yeah, one more option was there. Okay, similar matrices have same eigenvalues. Yeah, this is an easy. Is this true or false?
Similar matrices have same eigenvalues. This is true.
Yeah, it is true because
Uh, Determinant because they have the same characteristic
yeah, the
equation.
same characteristic equation. So eigenvalues are same. Like eigenvalues are solutions of the characteristic equation. Since same characteristic equation, so that eigenvalue should be same. Okay. Okay, now using this we can do like one more application of the spectral theorem. Okay, so I will give the question. You just see, like you have to use the spectral theorem here. Uh, if A is a real symmetric matrix and the only eigen only eigenvalue of A is lambda is 1, then prove that A is the identity matrix. Okay. So why I have asked you to use the spectral theorem, because it is given A is real symmetric matrix. So we know that, but we know
Uh,
what does the first statement of the spectral theorem says? If A is real symmetric matrix,
has real.
It is diagonalizable or not?
Yeah, it is diagonalizable.
Yeah. What it says, it is diagonalizable, so it can be written as P inverse dp for some invertible matrix P. And actually, it says one more thing. We don't need that. What is this P actually? What is specialty with the P?
It's invertible.
It's invertible, okay? It's orthogonal, right?
Hmm. Yeah.
Yeah, just check the theorem statement again. Yeah, it's orthogonal. Okay, we don't need this statement, whatever. We just need A equal to P inverse dp. Okay, now, uh, what is the given condition? Only eigenvalue of A is lambda equal to 1. Okay, now can you say what is D?
D will have one on the diagonal.
Yeah, then what is the
Identity. Yeah.
identity? So what is A?
A is also identity.
Yeah, that is what we want to prove that A equal to I. So this is just one application of the spectral theorem. So this is what we are using. Even the orthogonality we are not using, just this condition like diagonalizability only we are using. And what we are using is for similar matrices that we have already proved in the last question. Similar matrices have same eigenvalues. Okay, so since A and D has same eigenvalues of D are 1. That implies D is identity. So A is P inverse P equal to identity. It's proved. Okay, so this is very simple. Any other one is having doubt? If any of you are is having doubt, please ask and clarify it. So if you are not asking, I may assume that it is like clear for you. Okay. Now the next question is, which of the following equation will not be satisfied by the matrix A equal to 1, 2, 3, 4. And the options are, okay. So I have already seen if we have some kind of like polynomial equation, we can just substitute the a square, a cube, everything and check whether like what is that f of a. Okay. So can you say, or is there any other way to find that? I mean, the question is whether this A is like whether A satisfies the given equation or which of the equations are satisfied. That means if I am substituting A to the given equation, it should be equal to 0. Okay, so equation is satisfied means it should be equal to the 0 matrix. That means A square minus 5A minus 2 should be, or 2A should be equal to 0. If it is true, then A satisfies the A, option A. Okay. Now, can you think how we can do, or how we can approach this problem without finding this A square? And okay, can we use the characteristic equation? Okay, let us check what is the characteristic equation here. Okay, what is determinant of A minus lambda I? It is minus lambda 2, sorry, 1 minus lambda 2, 3, 4 minus lambda. Okay. Now, can you say whether the metric satisfies the first equation or not? In the beginning of the class, I have started, like not started, I have mentioned this. Whether I satisfies its characteristic equation or not. If f of x is the characteristic equation of some matrix A, then f of a equal to 0. Okay, this is a theorem. You haven't studied the theorem in the syllabus, but it is a very important and helpful theorem. And okay, of course we can omit the proof now. So using this result, can you say what is a square minus 5a minus 2i?
Yeah, actually, this equation is exactly the same as what is the given equation.
Yes. What is the given equation? It is same as the given equation is actually the characteristic equation, right?
Yeah,
Yeah. So what should be a square minus 5a minus 2i?
0.
It should be 0.
Yeah.
Okay. So the first one is satisfied. Now let us see B. What is B? X cube minus 5x square minus 2x. So we need to check a cube minus 5a square minus 2a equal to 0 or not. So what do you think?
Yeah, this also,
Uh,
because if we take out A, then
yes, if you are taking out a, this is a square minus 5a minus 2i. So this term is actually 0, 0 matrix. So 0 matrix into a means it should be equal to 0. Correct? Okay, before going to C, let us see D. What D says is x cube minus 6x square plus 3x plus 2. So we know that the characteristic equation is x square minus 5x minus 2. Okay. Now, if the characteristic equation is a factor of the given equation, that means if I can write it as some term like some g of x into the characteristic equation x square minus 5x minus 2, then it will be equal to 0, right?
yeah,
Is that clear? Yeah. So, only thing is we need to check whether it contains the characteristic equation or not. So, we can use the usual division. So, you know the division, right? Do you know the division just like this? Hmm? Anyone?
ma'am, once if you can just quickly tell us, I mean,
Okay, okay, you haven't seen this kind of division.
no, is it like simple? Say we take X, uh,
Yeah, exactly the same way how we use the usual division. If I am taking x, what should be the here? It should be x I am multiplying with this term. Okay,
yes,
as usual.
mm,
X cube minus 5x square minus 2x. Okay, so it should be minus x square. Are you able to follow this? That means
yes,
minus x square minus minus 5x square. So minus x square, and this is
plus 2.
no. Here it is
My,
3x minus minus 2x. So 5x, right? Okay. So what I am doing is all the same kind of powers I am subtracting. Minus x square minus minus 5x square. So I got minus x square. Now 3x minus minus 2x. So it is 5x. 2 minus 0. Here nothing is, like constant term is not there. So it is 2. Fine.
mhm.
Yeah. Now what should be here? The next term with which? think I should multiply so that I will get minus x square plus 5x plus 2?
Just one
1 or minus 1?
minus one.
Yeah, it should be minus 1, right? Minus 1 into x square minus 5x minus 2. I will get exactly this same value. Okay. So it is like remainder is 0 here. Okay. Remainder is 0 means what we will write? Just as the usual division. 6 square plus 3x plus 2 is x minus 1 into x square minus 5x plus 2. Okay. Now this is our characteristic equation. Sorry, this is 5x minus 2. Okay. Now, now what we can say about a cube minus?
Yeah, that will also satisfy.
So it should be equal to 0. Yeah. So the question was which will not be satisfied by the matrix. So we got A, B, D. Both all are satisfying. So this is the answer. Okay. I am just eliminating the options. Hmm? Yeah. One thing is you can verify this a square plus a plus I not equal to 0. That thing you can verify one thing. Okay. Maybe you can verify a square plus a plus I is non-zero. Or simply you can see this actually does not contain the any of the characteristic or eigenvalues, characteristic roots. Uh, I cannot see in general. I cannot say the full characteristic equation is a factor of the given one. Okay, actually, there is a smaller term called this minimal polynomial. Okay, minimal polynomial is a factor of characteristic equation. The only thing is we need to check if I have given if f of x is given and there exists a concept minimal polynomial, and this minimal polynomial is a, you don't need to go deep into this kind of thing. That is why I'm just using that elimination method, like that removing the wrong options. Minimal polynomial is a factor of f of x, then we can say f of a equal to 0. Okay, now uh, note that minimal polynomial is a factor of characteristic polynomial. That means, for example, if x minus 1 square into x minus 2, if this is the characteristic polynomial, minimal polynomial can be x minus 1 square into x minus 2, or it can be x minus 1 into x minus 2 also. Okay, so all the factor x minus 1, x minus 2, like separate factor should come at least once. More than once also possible, but it cannot exceed more than the characteristic polynomial. So it depends on the matrix. So these two are the possibility for the minimal polynomial. Okay. So as you haven't studied about minimal polynomial, we cannot uh, see further about this kind of things. So we can leave this question just by checking this. These three satisfies the ABD satisfies. So C is the answer. That is enough as of now. Is that clear for everyone? Not about this minimal polynomial. The other question.
Yes.
Yeah. Okay. So the next question is A be a 3 by 3 matrix with the eigenvalues 1, 2, and 3. Then first question is prove that a power 4 equal to 6a cube minus 11a square plus 6a. Second question is A invertible? If yes, find the A inverse in terms of powers of A. Okay, so whatever, the second option is actually one application of the characteristic equation and all. So before that, what was this 6A? Okay, so if we have some kind of polynomials in A, we should start the question with finding the characteristic equation. So we know the metric satisfy its characteristic equation. So find the characteristic equation, put the matrix in that instead of x, put the matrix in that, and then we can do all kind of operations there. So from there actually we will get this kind of equation. So in question, if you are seeing some kind of equation like this, the thing you have to do is find the characteristic equation. Okay, so what is the characteristic equation here?
We don't have the, so a minus lambda I only we can put, right?
But we have some other information about the matrix here. What is the question?
Okay, okay. 1, 2, 3. So it
Yeah.
is lambda minus 1 into lambda minus 2 into lambda minus 3.
Yeah, I hope everyone is okay with that, because 1, 2, 3 are the eigenvalues. What is characteristic equation? Either we can find determinant of a minus lambda equal to 0. Why we are finding that? To find the eigenvalues. But we already know the eigenvalue. Eigenvalue means root of the characteristic equation. So we are doing the reverse process. Lambda minus 1, lambda minus 2, lambda minus 3. So we will get lambda square minus 3 lambda plus 2 into lambda minus 3 equal to 0. So lambda cube. Okay, so I'm not going to the calculation. So whatever we are getting is lambda cube minus 3 lambda square. Okay, you can just check the calculation later. I hope it is correct. 11 lambda minus 6 equal to 0. Yeah. Now, uh, now how you can prove the first option? No, it is easy.
Actually, ma'am, the characteristic equation is coming as minus 6 lambda square.
Okay, okay. Maybe I might have done some mistake. Let me check once. Until this is it is correct, right? So lambda cube minus cube minus 3 lambda square plus 2 lambda. Yeah, that is 6. Is this okay now? Any further mistake? Is this okay?
Yes, yeah.
Yeah, okay. Yeah, so yeah, now can you say anything? Yeah, can we prove the first one now?
Yeah, yes.
Yeah,
So we take a out of the a common in that.
a out of the
Like we, if we take a common of the first equation, then it will
actually,
become,
yeah. Don't start from there. We should end there in the this equation, because that is what we want to prove. Okay,
okay,
so start from the characteristic equation. There we are taking a common outside, means in characteristic equation what we should do?
yeah, multiply by lambda.
Lambda, that's enough. So what we will get? Lambda power 4 minus 6 lambda cube plus 11 lambda square minus 6 lambda equal to 0. Fine. Now we can substitute the value here, right? Or we can directly write lambda power 4 is 6 lambda cube minus 11 lambda square plus 6 lambda. So this equation, A should satisfy this equation, correct? So it should be a power 4 equal to 6a cube minus 11a square plus 6a. Yeah, correct, right? So that is what we want to prove. Okay, clear for everyone? Okay, then what about the, now we don't know what is A. So adjoint A, like adjoint A by determinant of A, or in any other way we cannot find A inverse. Okay, and we don't want the explicit form of A inverse. The question is, what is A inverse in terms of powers of A? So just the question is how we can use any of the equation here. Like we have got so many equations here. Any of the equation, using any of the equation, can you find what is A inverse in terms of some I plus a square, like in powers of A? That's what they're asking. Are you getting? So this is the characteristic equation. Okay. So we can substitute A to 1, right? What we will get? A cube minus 6a square plus 11a minus 6a equal to 0. Okay. From this, can you say what is A inverse? A inverse means A into A inverse equal to identity, or A inverse into A equal to identity. Any of this is, like if any of this is satisfied, we can say whatever here it comes, that is A inverse. So my question is, extracting A and have some term, then the multiplication should be equal to I. Now can you think what is A inverse?
If we just put I is equal to A into A inverse, then like 6I is equal to
Yeah, 6i equal to,
6I is equal to A cube minus 6A square plus
hmm,
11A.
yeah.
And
Now what we can do?
like write I as A into A inverse. And then
Will it help? What we want? Sum A into A inverse equal to I. We already got I in the one side.
we can just multiply by I A inverse on both sides,
We can multiply
right?
with the, yeah, A inverse.
Yeah.
Yeah, that is fine. Otherwise, okay, that we can do. What we will get is 6A inverse is A cube minus 6A square plus 11A into A inverse. Okay, that means A square minus 6A plus 11I. So from this we can take 6 to this side. 1 by 6 into A square minus 6A plus 11A. Okay, one way is that way. Otherwise what we can do is I equal to 1 by 6 into, I am taking A outside from here itself. From this equation itself I am taking A outside. So what we will get is A square minus 6A plus 11I. Okay. From this directly I can say if this is A, and if I am taking 1 by 6 into this as A inverse. So this is A into A inverse, where A inverse is 1 by 6 into A square minus 6A plus 11A. Okay, both are same. One is just multiplying A inverse in both side, or take the A outside and whatever remaining term is A inverse. Both are same actually. Okay.
Mm.
Yeah. So this is one more application of the characteristic equation to find the, like, it won't be easy, like in higher order matrices actually it won't be easy to find the inverses. So we can use this, like you can just multiply this a square a cube, and Using this we can find A inverse. And one more positive thing is, if A is diagonalizable, again A square or whatever the power we are getting, it is very much simplified in terms of diagonal matrix. So in that case, finding A inverse is much more easier. So these are all the uh, applications that we can use in the like very complicated calculations. Okay. Yeah. Now one question is that, okay. Find a linear transformation from R2 to R2 such that range of t equal to null space of t. Range of t is actually a subset of this R2, correct? And the null space of t is a subspace of this R2. Okay. So what I am asking is, both the subspace, both are actually the subspace of R2. So both spaces are equal. That is, range T space and the null space of T. Both are same subspace of the R2. Okay. Can anyone construct the such a linear transformation T from R2 to R2? Yeah, we can solve this by step. How we can define T? A T is uniquely determined by the value in the basis, right? What is the basis of R2?
0110.
Yeah, this is the standard basis. Standard ordered basis is 1001. Okay. And if I know the value of T of 10 and T of 01, can you uniquely determine the T?
If we know T of 10 or T of 01,
Hmm.
yes, we can.
We can, right? Because
Yeah.
if I have some value T of xy, I want to find at some arbitrary point in R2, T of xy I need to find. But I will write T of x into 10 plus y into 01. This is fine, right? Since T is linear transformation, I can write x into T of 10 plus y into T of 01. So what I am saying is, if I know this value and this value, then T is uniquely, like T is defined for all the points in R2. Fine.
Mm.
Okay.
Yeah.
Now my question is, range of T and null space of T are equal. Like we need to find such a T. First of all, what can be the dimension of range of T and null space of T here? Both are equal means they have same dimension. Is that fine?
Yes.
Okay. So dimension of range of T and dimension of null space of T. It is a subspace of R2. So what are all the possible dimension of subspace of R2? What is the dimension of R2?
It's infinite. Like it's so many, right?
No, no,
I
no. Dimension of R2 means the number of elements in the basis.
Okay. Yeah.
Correct? Yeah. So what's the dimension of R2?
Dimension of R2 is 2.
Yeah, because two elements are there, which is linearly independent and spans R2. Correct? So
Mhm.
if you know that range and null space are subspace of R2. Okay. Now, what can be the possible dimension of this range and null space?
So since range is R2 itself, its dimension will also be 2.
uh, ranges up to itself. Why
Like,
ranges up to itself? See, suppose range is up to itself. Then what we are saying, dimension is 2, correct?
yeah.
That means dimension of null space is also 2. Okay.
Mm-hmm.
Now, will it be a contradiction to rank nullity theorem? What is rank nullity theorem? Rank plus nullity should be equal to dimension of R2. Like, what is this space? The dimension of this space. What is the rank? Rank means dimension of range. Here rank is 2, nullity is also 2. Nullity means,
Then null space
yeah,
how
dimension
many?
of null space. So,
Yeah.
if you are saying both are 2, then it is equal to 2. What is this? This is contradiction, right?
Mm. Yeah.
See, for example, if our map T is 0 map, what is the range? Range means the all values to which T is mapped. If I am mapping T only to 0, that means T of xy equal to 0 for all. Then what is range? Only 0 element, right?
Mm-hmm.
Okay. Are you able to follow? Why range? See, what you said is range is full R2.
Yeah, I'm just trying to understand.
Okay. My question is T from R2. Let it be like some other notation I will take. S from R2 to R2 such that S of xy equal to 0, 0 for all xy. This is linear transformation, right? It's a,
Mm-hmm.
okay. Now, what is range of S? Range of S by definition is the set of all xy such that xy in the domain space R2. This R2 is the domain space. So what is this set of all 0, 0? Okay. So this range is a proper subspace of R2 here. Okay.
Mm.
Yeah. Now, if I am taking S as the identity map, suppose S naught I am taking as R2 to R2 such that S naught of xy equal to xy. Now, what is range of S naught? What are all the images of S naught?
The complete R2.
Yeah, complete R2.
Yeah.
Yeah, this is complete R2. So, what I am saying is range can be any subspace of R2. It is always a subspace. It can be any subspace of R2.
Mm-hmm.
Okay. Okay. Now
Mm.
again coming to what we were talking. Yeah. So this is not possible, right? Dimension range of T, dimensional space of T equal to 2. That is not possible. Is that clear? Because
Mm.
it contradicts the rank nullity theorem. Fine. Any doubt?
Yeah, actually, it's not like completely clear to me.
Okay. So is this step clear? First step, dimension of range of T and dimension of null space of T equal this much.
This is a given condition, right?
Yeah,
Like,
given condition is both space are equal. Range of T and null space of T are equal. Same space.
yeah.
So same space means its dimension should be same.
Yes.
Yeah, that is why I am writing dimension of range of T equal to dimension of null space of T. Okay, let me
Correct.
write again. So dimension of range of T is the rank of T, and the dimension of null space of T is the nullity of T. This we know. Now, we also know these are subspaces of R2. Correct?
Yes.
Yeah, what are all the subspaces of R2?
Uh, it will depend on how the mapping is, right?
No, no, no. Subspace does not depend on the mapping. Subspace means a subset of R2 which itself is a vector space.
Yes.
Okay. For example, R2. What is R2? It is span of 1001. Correct?
Yes.
Now, if I am taking mm, S1 equal to span of 10, is this a subspace? I'm taking all linear combination of 10. So it will be a subspace, right?
Mm-hmm.
Because, okay, you can check. 10 is a linearly independent set, obviously it is a non-zero vector. And also, we are taking all the span. So all the linear combinations are taken. So it is a subspace. What is the dimension of S1? Because this is the basis. This is a linearly independent set and it spans S1. Okay. What is the dimension of S1? Dimension of S1 means the number of elements in the basis of the space S1. And the S1 is actually span of 10. That means 10 itself is enough to generate the whole space because I'm taking 10 and 20, 30 and in between 1.50. That means the whole line I am taking. So this whole line, so this is 10, sorry, not this line, the whole x-axis. So this is my 10. I am taking all the multiples of 10. So the whole line it will come, right?
Yes. In the subspace.
Yeah, in
Yes.
the subspace. So if I am
Okay.
adding two elements here, again it will be in this line itself,
Mm-hmm.
multiplying. So this is a subspace, there is no doubt. And it,
Yes.
just 10 is enough to generate this whole space. Correct?
Mm-hmm.
So
Mm.
this is a basis for S1.
Okay.
Okay, so that is why I am saying dimension of S1 is 1.
But
Okay.
dimension of S1, because we have one element, is that
Yeah, yes.
because the basis
Because,
is one set.
yeah, basis of S1 is set to 10. That means only one element is there.
Okay.
Actually,
Okay.
set to 20 is also a basis. Any element is a basis except 00. Any element in
Mm-hmm.
the line is a basis because we can take any other element as a linear combination of this one.
Yeah.
Okay, so the only subspaces possible in R2 is all these kinds of lines.
Mm-hmm.
Okay, this line, like lines going through the origin, not every lines.
Mm-hmm.
These are all the one dimensional subspaces of R2.
Mm-hmm.
Okay, so R2 has subspaces, uh, all lines, the one dimensional subspaces,
Mm-hmm.
and the R2 itself. So every space itself is a subspace. Correct?
Mm-hmm. Yeah.
And what can be the third possibility? The 00 means just the zero element. Its dimension is 0. That is by convention. Okay.
Mm-hmm. Yeah.
So these are all the possible subspaces of R2. Okay.
Mm-hmm.
Now, uh, where is it? Yeah. What we were saying is dimension of range of T and the dimension of null space of T are equal. Correct? So,
Yeah.
uh, since it is a subspace, what are all the possible dimension for this? Now,
Okay. So dimension is one, right? That's what we found, that only one element is there
uh,
in the subspace.
no, no. See, if we are taking a space, a vector space like R2, so uh, as of now, I didn't tell anything about the T map. Okay, I am just saying the subspaces of the vector space R2. So subspaces possibility are either zero dimensional space 0 0, or one dimensional space any
Yes.
line, and two dimensional space R2 itself. Okay, keep that aside. Now I am coming to the linear transformation from R2 to R2. Okay, now for any linear transformation, range is a subspace of the R2. Means T from R2 to R2. Range means set of all elements in the second R2 such that T of xy means set of all T of xy. Okay, and the range is a
Mm.
subspace of R2. That means range can be either zero dimensional subspace 0, or it can be the one dimensional subspace, that is any line, or the range can be whole R2. Is that okay now?
Yeah.
Because it is a subspace. In the same way, null space is a subspace of the first R2. T from R2 to R2. In that first R2, null space is a subspace of the first R2. So again, since it is a subspace, it can be either zero dimensional subspace, one dimensional subspace, or two dimensional subspace. These are the three possibilities, correct? So
Yeah.
as of now, we just know it can be 0, 1, or 2, correct? Its dimension.
Yes.
Yeah. Now, why it is not 2? That is what I was doing with the rank nullity theorem. Okay. If dimension of range of T equal to dimension of null space of T equal to 2. What is the contradiction we are getting? So this we will say rank of T. This is another name. And this is nullity of T.
Mm. So rank plus nullity will be greater than
Yeah, rank
dimension.
plus nullity will be 4, which is greater than 2. But it should be equal to 2.
Yes.
So contradiction to rank
Mm.
nullity theorem.
Okay.
Now, can it be both 0? Of course, it should be equal. Can it be both 0?
Yeah. X1, like the domain has 0 0, and then it maps to 0 0.
No, no, no. I am asking, can dimension of range T equal to dimension of null space of T equal to 0? Again, think with the rank nullity theorem. What is rank nullity theorem says?
Rank plus nullity should be dimension of.
Nullity should be equal to dimension of R2. That is 2.
Yeah.
So here again it is a contradiction, right?
Mhm.
This is not equal.
Okay.
Yeah.
Hmm.
So what is the remaining possibility?
One, I think
Yeah.
that.
Both should
Hmm.
be dimension of range of T should be equal to dimension of null space of T should be equal to 1. So we will get 1 plus 1 equal to 2.
Mhm.
Okay, so we removed the first two possibility. Both are coming 2, both are coming 0. Now, what we can say is, so what was our question? The question we started with, find a linear transformation T such that range of T and null space of T are equal. Correct?
Yeah.
Yeah. Now, we got both have dimension 1. That means both should be some line, or both should be span of some element, say 1 0. There is no specialty with 1 0. I am just taking 1 0. Okay. What I want is range of T equal to null space of T equal to span of 1 0. Okay, so it has dimension 1, right? I am taking a space with dimension 1 and I am trying to construct a linear transformation such that range of T and the null space of T are the line x-axis. This is what is actually x-axis, correct? Span of 1
Yeah.
0 means, yeah. Okay. Now, uh, as I told, there is nothing special with span of 1 0. You can try with span of 0 1 also, or try with any other uh, like any other subspace. Okay, you can do it as a homework. Okay, now how we can construct the so as I told already, if T of 1 0 and T of 0 1 are determined, we can say what is T of xy. Correct?
Mm.
Yeah. Now can you say what is T of 1 0? So we have this condition now. I am taking this. Can you say what is T of 1 0? Does 1 0 belongs to null space of T? Okay. I am saying T of 1 0 is 0 0. Can you say the reason? Okay, what is null space of T? From this star you can read what is null space of T. Okay, before that, what is the definition of null space of T? Do you remember?
Is it
It is
domain? Mm.
set of all elements which is going to the zero elements. Correct? Set of all xy such that T of xy equal to 0. Is that okay?
Okay. Yeah.
Yeah. Now, from star, what it is given that this null space is span of 1 0 from star. Okay,
Hmm.
what does this mean? This means T maps all elements in the null space to 0. This means the set of all elements which is mapped to 0 under T. That is the null space. So this is equivalently saying all elements in the null space are going to 0, correct?
Yeah.
Yeah. 1 0 belongs to null space. Any doubt in that?
No.
No. So what is T of 1 0?
Yeah. So it's 0 0.
Yeah, it is 0 0. That is what I have written here.
Okay.
Okay. Now, can you say what should be T of 0 1? Now, you need to use this condition here. See, null space of T, range of T is not this condition. Okay, yeah, altogether actually you should use. What is range of T? It is given span of 1 0. We are taking range of T as span of 1 0.
Mm.
Okay, now uh, if I am taking T of 0 1 is 0 0, is this possible? That means
Yeah.
0 1 is also, no, correct? Because 0 1
Yeah.
is also going 0, that is not possible.
Mm.
Okay, now I am taking T of 0 1 is 0 1. Is this possible?
Uh, I'm not sure.
Yeah. My question is T of 01 is 01 means 01 belongs to range. Any doubt in that?
No, no.
Yeah.
Yeah.
Now, what is our range?
Range is a span of
Span.
1 0.
Yeah. So now
Yeah.
tell T of 01 is possible or not? So T of 01 is 01 means 01 belongs to range. And this range is span of 1 0. Correct? That means 01 belongs to span of 1 0. Is that true?
No, just one clarification. So we are saying range also a span of 1 0, right?
Yeah, range also span of 1 0. So I need,
So will 0 1 belong to the range? Because elements of the span will look similar to the basis element, right? Like
yes.
1 0, it
Yeah,
will
that is
be
what I
1,
am
2
asking.
0.
Is this possible or not? That is what I am asking. Is
And
this
no,
possible or is this possible? No, right?
no.
Okay. So we found T of 01 cannot be 00 or 01. So
Mm.
can you say any number, any element in R2 such that T of 01 is that element? Like I need some element here such that range of T is the span of 1 0. That is what I want, correct?
Mm-hmm.
That
Yeah,
means,
so
yeah,
1 0 itself we
of
can take
course.
or any multiple. Yeah.
Yeah, any multiple. Okay, 1 0
Mm.
itself we can take. That is the very easy thing.
Yeah.
Yeah. Now, what we got from here, we got all the 1 0. From here, what we are getting is 1 0 and all the multiples of 1 0. That is span of 1 0 is null space. Okay. And since 0 1 is mapping to 1 0, from here we can get the span of 1 0 is range. Okay, so that was our question. Construct a linear transformation T such that range and null space are equal. Okay, so we constructed the transformation T. Is that fine for everyone now? Okay, now, okay, we haven't done completely. Then what is T of xy? T of 1 0 is 0 0. Okay, T of 0 1 is 1 0, correct? So that is what we have written. So what is T of xy? In basis we have defined T. Okay, this I have told in the beginning of the question. How we will write T of xy. What is xy? X into 1 0 plus y into 0 1. Now you can say what is T of xy.
Yeah. Uh, x into t of 1 0,
Yes.
that is 0, 0 plus y into 1 comma 0.
Yeah, that is x into 0 0 plus y into 1 comma 0. Okay, so it will be y 0, right? Hmm?
Yeah.
Yeah.
Mhm.
Okay, so hmm, they wanted to do. Okay, so what is the metric representation of this T? You can do very quickly that. How we will do the metric representation? First we will find the value at the basis element. T of 1 0 is 0 0. That is 0 times 1 0 plus 0 times 0 1, correct? And T of 0 1 is 1 0. That is 1 times 1 0 plus 0 times 0 1. Then what we will do? Metric representation of T is this term 0 and this 0 we will write in a column 0 0 1 0. Okay, this is how we write the metric representation. Okay, now what do you think? T is diagonalizable or not? Okay, let me write this as here. Is A diagonalizable? Okay, that you can check actually. I mean, we have seen so many questions like that. You can check it, right?
Yeah.
Yeah. Yeah, it's already 8 o'clock or so. So here A will not be diagonalizable. Prove it. Okay. Actually, I have taken a lot of time for this question, I think. Yeah. So shall we stop now? Actually, I had some more
Yeah.
things. Okay,
Thank you,
maybe
ma'am.
remaining question we will discuss next week. Some more questions are there. Yeah. If you have any doubt, this is all like we have seen in the some previous weeks. You might have forgotten things. Yeah, okay, you can just refresh the things. Yeah, nothing else.
Mm.
So, if any doubt is there for anyone, yeah, please ask now. Otherwise, we can stop. Yeah. Okay then. Shall we stop?
Yeah.
Yeah.
Thank
Okay.
you.
Yeah.
Good
Thank
night.
you. Yeah, we will meet next week also. Bye.
Mm. Bye.